Okay, this is going to be our second video on statics and torque. And as I mentioned in the first video, we don't have anything really else to go over as far as new physics. What we're going to be doing here is applying the ideas that we talked about in the first video to solving some problems here. And so this is going to be our last video in this series. So this series is going to be a very short one, only 2 videos. And so this will sort of close out this module. So as I mentioned, we're going to do some examples in this video. I have 2 examples set up. This first one's pretty short. This one is sort of designed to show you guys how easy a problem like this can be if the circumstances are right here. Like, we don't even really have to apply some of the conditions of equilibrium here, and we'll be able to get to our solution. And the second problem is set up to sort of show us that well, it's a little bit more complicated of a problem, and that we can make it easier or more complicated on ourselves depending on where we choose our pivot to be. So we're going to solve this second problem in 3 different ways, and we're going to see that it gets easier or more difficult depending on the choices that we sort of make. Okay. So let's get started with this this first problem here. This one is directly from the text. This is I think this is the problem number 10 from the text. So what do we have here? We have a 17-meter high wall, which is 11 meters long. It's under construction, and the bracings are shown in the figure below. So I didn't copy the figure directly from the text here. I figured it'd be easier to draw it. So this is meant to be the wall here. This is our wall standing up, and then it's braced by 10 different braces, these little wooden sticks that are sort of holding it up. Okay, so the wall is in stable equilibrium without the braces, but it can pivot about its base, so it can pivot about the base down here. And we want to calculate the force exerted by each of the 10 braces if a strong wind is exerting a horizontal force of 650 newtons on each square meter of the wall, assuming that the net force from the wind acts halfway up the wall. Okay, so I've drawn the force of the wind here, and we're gonna assume that force of the wind is also acting halfway up the wall. So 8.5 meters from the base, right where our supporting stakes here are hitting the wall. Okay, so we're going to assume that the net force from the wind acts halfway up the wall, and that the braces have sort of a stabilizing force that's parallel to the brace, right? So we have our wooden braces over here, and this FB that I've drawn here, this is our force from the braces. It's parallel to these braces, which hit the wall at a 35-degree angle, right? So we can see that there. Okay, so we're neglecting the thickness of the wall, and we just want to calculate. Well, what does the question ask us? The question asks us to calculate the force exerted by each of the 10 braces, right? So let's take a look at this. Now, we could think about this in terms of torques. We could set up a sort of positive direction for our torque in this direction, and then take a look at all the torques. But we just have to realize that really there's going to be no torque on the system, because while we have our force of wind hitting this wall halfway up the wall, we also have the force supplied by our braces hitting the wall halfway up the wall. So really, if we thought about this very simply, we could think about the wall. We just have the force of wind this way, and the force of the braces, but this is just the perpendicular part of the force of the braces pointing that way. So really all we need to do is balance those 2 forces. There will be no torque. We just need a 0 net force being applied to this wall, and we're pretty much all set to go. So maybe I'll leave this little drawing here. And so the first question is, well, what is this force of the braces perpendicular to the wall, right? Well, just by using all the same trigonometric tricks we've been using for the whole course here, we know that FB perpendicular is just going to be FB sine theta, right? And so we have so we're going to have no need to look at any of this sort of torque stuff, right? Because now we know what FB is. We can easily say that we need so our first equilibrium condition tells us that that F net needs to be equal to 0, and our F net here is going to be FW minus FB perpendicular, right? And so this tells us that FW equals FB perpendicular, and if we substitute in our expression for FB perpendicular, excuse me, we're going to end up with the following expression. And if we want to solve for FB, we can do that quite easily. Right. And so now it's just a matter of figuring out what this FW is, right? So we have 650 newtons per square meter on the wall, and our wall is 17 meters high and 11 meters wide. Well, so let's just find the total area of our wall. We have 17 times 11. That's going to be 170, 187. So meters squared, right? And we need to multiply this by so the force of the wind, the total force caused by this wind on the wall is going to be equal to 187 times 650 newtons. I don't have a calculator. I have the number here. That's going to be 121,550 newtons. Okay, so that's the total force on the wall, but we know that we have 10 stakes holding up this wall. So we can just think about the force of the wind divided by 10, right? Because it's going to be supported by 10 of these different stakes, right? So we can simply, I mean, we could either divide the number by 10 later when we think about FB, or maybe we can divide it now. Let's say. So let's say we let this go to 12,155 newtons. This is per and what do we call them? Brace, right? So each one of our braces needs to counter that much of the wind's force, and so we can simply substitute this number in for the force of the wind on each single brace, and if we do that, we end up finding that the force exerted by each one of those wooden stakes is simply going to be 1,200 or 12,155 divided by the sine of our angle, which was 35 degrees. If we do that calculation, we're going to end up finding that that the force that each one of these stakes is exerting in that direction upwards and to the left is going to be equal to what was it? It's about 21,000. 1, 2, 3. Yeah, it's about 21,000 newtons. Okay, and I've done some rounding there. Obviously, I think it would be like 21,190 or something. But basically, that's the answer to our question. Okay, so we can see in this example here that it's actually a lot simpler than it may seem originally, right? Like we had a pivot down here, so we may be thinking about doing all sorts of things with our second equilibrium condition. But in this case, we don't need to, and we can get to the answer quite quickly just by thinking about sort of how this whole physical system would sort of work itself out. Okay. Let's take a look at our second example now. This example is going to be a little bit longer because I'm going to basically solve it 3 times in 3 different ways. We're going to see that some of the ways that we're going to choose to solve this are more difficult, lead to sort of more work for us to do, and other ways are easier, but in the end they all lead to the same answer. So you're always going to want to try to choose whichever way is easiest. It's not always simple to tell sort of when you start out which way is going to be easier, but more experience with it will sort of lead us to make better choices about that. Okay, so what do we have here? This is supposed to be a person here, so I've drawn that person. We have a person holding a pole horizontally in equilibrium in the configuration we see here. We want to calculate the magnitude of the forces exerted by the person's hands on the pole. Okay, and so we have some distances worked out here. We have the mass of the pole. We're going to assume that mass is evenly distributed over the whole pole. So we can think of the force of gravity exerted on the pole as a sort of force here. So I'm just going to draw a vector here, so we can imagine that this is the force of gravity. which is simply equal to mg here, acting downward on the pole. And so we may not really know, well, we may in this case, but in some cases we may not really know what direction to draw our forces in, right? We're not sure what direction the forces applied by the hands have to be to keep this thing in equilibrium. So we kind of can make a guess on the direction that these forces are going to be in, and if we're wrong about the direction, at least in an up and down sort of sense, we're going to find an additional minus sign that's going to sort of correct the guess that we made. So I'm going to make a guess here. I'm going to call this one FC for a reason that we'll see in a second. So this is the force of the person's left hand if we imagine they're facing us. And I'm going to call this FB. I'm going to assume they're both upward. We're going to find that we're wrong in that assumption later on, but that's fine. We're going to see how it all works itself out. and so with these distances, what do we have? We have the person's. So we have the pole here. We have the person's right hand 1 meter from the beginning of the pole. We have the person's left hand 1 meter from their right hand, so 2 meters from the beginning of the pole. And then an additional ½ meter from that pole, we have the center of mass of the pole, which is where we're looking at our force of gravity acting downward, right? And so I'm going to label a few points on this post, and we're going to consider a number of these different points as the pivots. So I'm going to consider this point here at the end as point A. I'm going to consider the person's right hand here, point B, the person's left hand, point C, and I'm going to consider the center of mass, point D. Okay? And so there's no natural pivot that we can sort of consider here, right? This thing is in equilibrium. It's not supported anywhere just by the person's hand, so it may not be actual. Well, we know it's in equilibrium, so it's not going to be moving anywhere. But we're free to choose the pivot that we would like when we're answering this question, and then work from there, right? So we can choose. Excuse me. I selected 4 different points here. We're only going to do 3 of these points, but we could select any point on this post, or any point anywhere really, and just choose that as our pivot. But in this case, we're going to start off by looking at point A, right? So we're going to think of point A out here at the very edge of the post as our pivot, and we're going to solve for FB and FC, the forces exerted by the person holding this as hands. Okay, so let's start off with that. We're gonna choose point A as the pivot. And spoiler alert here, we are going to discover that this is a pretty poor choice, but let's do the calculation anyway and see how this turns out. So I have some numbers here, but we'll work through it. Okay. So if this is our pivot, if A is our pivot, then we're gonna have a couple of distances here that we need to consider. We need to consider the distance from A to B, the distance from A to C, and the distance from A to D, because those are going to be the points at which our forces are applied, right? So we'd have one distance here. This would be, I'm going to call this RB. So this is where our force vector from our right hand is being applied. I'm going to call this distance out to C, RC, and this final distance all the way out to D will be RD. Okay, oops. Okay, so those are our 4 distances, and now let's apply the second equilibrium condition. So our second equilibrium condition tells us that our net torque has to be equal to 0. But we can see that our net torque is going to be, oh, and I should mention here that we're choosing, I'm going to choose this, as I often do, I'm going to choose the counterclockwise direction as our positive direction for our torque, right? And so we can see that FB and FC are acting in the positive direction if we think of a pivot at A, and FD, or our FG here, which I'll call FD here just for simplicity of labeling, is operating in the negative direction, right? So we're thinking of this thing pivoting around A. FB and FC will sort of help it go in the counterclockwise direction, and FD will push in our negative direction or in the clockwise direction. Okay, so as we label this, we're going to end up with torque B plus torque C minus torque D. Right, again, following the positive direction of that we've chosen here, the counterclockwise positive direction. Okay, but note that all of our theta, so I haven't drawn any angles in here, right? All of our angles between our R's and our forces are always going to be 90 degrees, okay, for this example. This is not true for every example, but in this case, all of our forces are perpendicular to our distances R, right, to these vectors that give us the distance R. And so we're going to find that we simply have theta equals 90 degrees in every case, which means that sine of theta is just going to go to 1 in every case, right? So instead of rewriting each of these taus with a sine theta in it, then setting it to 90 and setting it to 1, I'm just going to skip that step, and we'll simply just set them to 1 right away. So we're going to find that 0 is equal to, well, it's going to be RB FB plus RC FC minus RD FD, okay? And so what's our goal here? Let's keep that in mind. We're trying to solve for FB and FC, right? The forces exerted by the hands of our person holding this thing, right? So let's start off solving by what we're solving for FB. So we can isolate FB here. We're going to find, so I'm going to isolate FB on one side. I'm going to move the C terms and the D terms over to the other side, divide through by RB. If we do that, we're going to find an expression that looks like this. We have FB equals 1 over RB, RD, FD, minus RC, FC. Okay? And so we've used our second equilibrium condition to solve for FB, but we can't solve this equation yet, right? We don't know what FC is. We do know what the rest of the variables are, but we don't know what FC is, so we need another expression for FC. Okay, let's use our first equilibrium condition. So F net is equal to 0. And again, if we think about the positive y direction here as this way, so if we think about that as our positive y direction, then we can see right away that we have FB plus FC minus FD acting in the y direction here. So FB and FC in the positive y direction, and FD in the negative, right? And this, if we maybe I should use more of the space on the right here. So if we reorganize this, we're going to see that FC is equal to FD minus FB, right? So we now have these two equations involving FB and FC, and the two unknowns are FB and FC. So we're in a position where we could solve this system, right? And that's exactly what we're going to do. I'm going to substitute. I'll call this equation 1. This one equation 2, and we're going to substitute equation 1 into equation 2. So 1 in 2 gives us, well, we're going to find FC equals FD minus 1 over RB, RD, FD minus RC, FC. Okay? And so now there's only, in principle, one unknown that we don't know here, which is FC. It shows up in a couple of spots here, so we need to rearrange this and isolate our FC. So the next couple of steps here is just going to be us trying to isolate our FC here. So I guess I'll do the steps. So we're going to end up with FC is equal to FD. So what am I doing here? I just want to distribute this 1 over RB everywhere, so we have our terms separated, so we can more cleanly work with them. Okay, so we're going to have FD plus the two minus signs cancel, RC, RB, FC, and now we want to slide the FC term over to the left, and so we're going to end up with FC times 1 minus RC over RB is equal to FD 1 minus RD over RB, right? And so maybe to clean things up, I'll multiply through by an RB. So we can see that we'd end up with RB minus RC equals FD RB. Oops, that should be a capital B. Let me clean that up. Minus RD, right? And so now we just need to divide through by the terms that are multiplying FC on the left here. FC is now equal to FD, RB minus RD over RB minus RC. Okay, and so now we can solve for FC. We just have to substitute in numbers. So we know that our FD, well, our FD is just our FG, which is just MG, which is just 5 times 9.8, right? And so we're going to find 5 times 9.8. And then we have this this ratio here. So we have RB minus RD. Well, what's RB? RB is simply going to be 1 meter, and RD is 2.5 meters, right? We can see that from here. Maybe I'll write that in. 1 meter. RC is 2 meters, and RD is 2.5 meters, okay? And so RB at 1 meter minus 2.5 meters, and then again RB minus the 2 meters from RC, okay? And so this is going to give us, what do we have? That's 49 times minus 1.5 over minus 1. And if we do that calculation, so the minus signs are going to cancel, we're going to have 1.5 on the top, and we're going to find that FC is equal to 73.5 newtons. Okay, so we found that our FC, the force exerted by the person's left hand, is 73.5 newtons, and it's a positive value, so that means that the direction that we chose for FC is correct. And we're all set there. We can now make use of our equation number 2, I guess, to solve for FB. So we can say equation 2, just slightly reorganizing it. We're going to move FB over to the left and FC over to the right. So it's going to be FB equals FD minus FC. And we can solve that right away. We know that that FD, again, this is just our force of gravity, which we kind of solved for here. So that's going to be 49 minus the 73.5. And if we do that calculation, we're going to find that we have minus 24.5 newtons. Okay, so that's our FB. So what is that telling us? Well, that's telling us that we have a 24.5 Newton force, but in the negative direction than we chose. So actually, the force that this hand will need to supply is actually a downward force of 24.5 newtons, right? So that minus sign is telling us that the FB upward that we chose here was incorrect, and that we need to actually apply a force downward, right? And so that's great. We've basically solved for the two variables that we are looking for, FB and FC. Okay, and so maybe I'll make a note here. Negative means down in this case. Okay, so this was the calculation with our choice of pivot at point A, but we're going to see that this problem can become much simpler. So we had a fair bit of calculation to do here, but we can see that this problem, well, we will see that this problem is made more simple if we choose a different point. So let's now choose point B as oops. Okay, so if we choose point B as our pivot, let's take a look at sort of what happens up here in the drawing. If we choose point B, then obviously our R values are going to change, right? Because we've shifted our pivot over. So if maybe I'll just draw it down here very quickly so we have it in front of us. But so assume this is our post. This is very poorly drawn, but we have our hand here, and this is point A, B, C, D, right? But now we've chosen B as our pivot, right? So this is our pivot, and so now RC will be this, and RD will be this, but RC is now just 1 meter, and RD is 1.5 meters, right? And we don't need to worry about RA because there is no force applied at A, right? So if we choose B, now it's true that there's still a force being applied at point B, right? But from the perspective of torque, right? Think about what the torque at point B is going to be. The torque at point B is defined as RB, FB, and I've drawn these B's in lowercase, but it should be RB, FB, sine theta B, right? Well, we've already said that these sines are all going to go to 1 because these are all at 90 degrees. But RB here would be the distance from B to B, which is really just 0. And so we have no torque being supplied at point B because we've taken that as our pivot, right? So we've, in a sense, eliminated from the torque calculation this one point, which is going to make everything much easier, as we're going to see here in a second. So let's start off as we did in the previous case, applying our second equilibrium condition. So our net torque is going to be equal to 0, but it's also equal to, well, again, so we're thinking of these as being FB in this direction, FC in this direction, and FD in that direction. And this is our positive torque direction, our counterclockwise. And we're thinking of this as positive y, right? And so let's add up the torques that we have here. We've already discussed why there is no torque from B, right? Because that's our pivot. And so we end up with a tau C minus a tau D, right? And think about that for a second. Our FC is operating in the counterclockwise direction for our torque here, so it's positive, and our FD is operating in the negative direction, so it's counterclockwise and comes in with a negative sign, right? And both of those need to be equal to 0. And so what does that tell us? Well, that tells us that they are equal to one another. So tau C equals tau D, and we can rewrite those in terms of their R values and the forces. So we end up with RC FC equals RD FD, right? And we're interested in solving for FC. We know what FD is, right? FD is just FG, which is just mg, which we already solved for a couple of times, which is 49 newtons, I should say. Okay. And so let's solve for FC. FC gives us RD over RC FD. Our RD in this case is 1.5, and our RC is just 1. FD we just said was 49 newtons, and if we do that multiplication, we're going to end up finding the same value again. Obviously, 73.5 newtons. That's our FC. Okay, so we just solve for it again. You can see that our solution for FC, in this case, what it took us 3 lines maybe. Over here, it took us significantly more to get to FC, right? And now we're also ready to get our FB, right? So FB is not involved in this torque calculation, but we still have the first equilibrium condition. So F net is equal to 0, and now we need to add up all the forces. So we have FB plus FC operating in the positive y direction, and FD in the negative y direction. This means we can right away solve for FB. FB is going to be equal to FD minus FC. And we already talked about what these are, so we know FD is 49, and we know FC is 73.5. If we solve for that again, we find an FB equal to minus 24.5 newtons. And again, why does it come in with this minus sign? Well, it comes in with a minus sign because, again, we've assumed that FB is pointing upward here when actually it's pointing downward, right? And that's what the minus sign is telling us again. I'm not sure that I should go through this again for pivot C. I was planning to. Okay, yeah, I guess I'll do it. So let's go through with pivot C as our choice here. Okay, so let me draw this diagram again. Okay, so we're choosing point C as our pivot. We're remembering that we have this set up here. This will be our center, so we'll have FD here, and this is point D. Then we'll have a hand here and a hand here. So it'll be point B, point C, point A. We have FB here, FC here. And since we're choosing point C, this becomes our RB equal to 1 meter again, and our RC is equal to 0.5 now, right? So if we just think about the distances from the original drawing, those are our distances, right? And so now our pivot, we've chosen point C as our pivot, right? So we're going to find that, again, tau C, which is equal to RC FC sine theta C, well, again, all these thetas are just 90 degrees, so that just goes to 1. And our RC is a distance from C to C, so that's just 0. So again, we find tau C is 0. And so we only need to really concern ourselves with the torques supplied by FB and FD, right? And so we need to be a little bit careful here, because since we've moved our pivot point to point C, we've sort of changed the direction as far as torque goes in which FB is operating, right? Like FB in the first part, where we assumed our pivot point was A, ended up being operating in the positive direction. But now FB operates sort of in this direction, right? We're going around that way. So FB is going to be negative. So let's take a look at our second equilibrium condition. We have tau net equal to 0, but now it's equal to minus tau B, right? Because tau B is operating in the clockwise direction, and tau D is also operating in the clockwise direction, right? And tau C we don't have to consider, because we know tau C is 0, right? So let's clean this up a little bit. We can move tau B to the left. We're going to end up with tau B equals minus tau D. Changing those into their R and F forms, we're going to end up with FB equals minus RD FD, right? Substituting in for the values that we know, or I guess maybe I'll solve for FB on its own. We have RD over RB FD, and this is going to be minus, so RD, oh, and I'm not sure why I labeled that C, that should be a D. So RD is 0.5 divided by RB, which is 1, and FD again is 49. So we end up with basically negative a half of 49, and so that's going to give us 24.5, right? So we find that FB is minus 24.5 newtons again, as we found before. And again, this is just telling us that we've chosen the wrong direction for FB. It's actually pointing downward, and we found the same value again. And we can very quickly see that using our first equilibrium condition, Fnet equals 0 equals FB plus FC minus FD. We can solve for FC. So FC equals FD minus FB. And if we substitute in values for that, we're going to end up with 49 minus 24.5, giving us a value for FC of what is it, 73.5 newtons, right? So again, we see the same result. So this was basically just showing us that no matter how we choose to do this problem, no matter where we choose our pivot to be, we're going to end up with the same values. In some cases, it's only a couple of lines. In other cases, it's more calculation. And this can get much worse depending on how complicated the problem is, right? So we want to be careful. Ideally, we want to try to, from intuition, choose what we think will be the least work, and in the end, no matter what we choose, we're going to find the same answer. It just might be more or less work, okay? And so that's going to conclude our series on statics and torque. We're going to be doing some more examples, obviously, in the assignments, but in the next video we'll be moving on to our next module. Okay, I'll see you guys in the next one.